In the world of high-stakes manufacturing, there's this hidden rule book. It's something that quietly ensures fairness, drives innovation, and shapes basically everything we use. So today, we're going to open that book and get to know ISO 3685. It all kicks off with a really simple question that's actually, well, pretty tricky to answer. If you've got two cutting tools, how do you prove, like really prove, with science, that one is better? I mean, without a common set of rules, it's just one person's claim against another. It's total chaos. So how do you find the actual truth in all that noise? All right, so here's our game plan for getting to the bottom of this. We'll start with what we're calling the comparison problem. Then we'll introduce the universal rulebook that was designed to fix it. After that, we'll get into the nuts and bolts of how it works, see its massive impact in the real world, and finally, look at how this one little rulebook is actually building our future. And that brings us right to the solution, right? A universal rulebook. The hero of our story is an international standard, a really specific guide for testing cutting tools, and it's called ISO 3685. So what is it exactly? Well, to put it simply, ISO 3685 is basically a global agreement on how to test the performance of single-point cutting tools. The kind used in just about every manufacturing process you can think of. It gives everyone a standard way to measure how long they last and how they wear down. It gets everyone speaking the same language. I love this analogy. Think of it like this. ISO 3685 is the official rulebook for the Olympics of cutting tools. It makes sure that when two tools go head-to-head, they do it under the exact same conditions. It's a perfectly level playing field. No shortcuts, no unfair advantages, just pure, honest, comparable performance. And that really gets to its core mission. The whole point is to make tests reproducible, so a test run in Germany gets you the same results as a test in Japan. It gives a super precise definition for what wear even means, tells you exactly how to measure it, and maybe most importantly, it just gets rid of all that random noise in the data. So how does the standard actually work? How does it manage to take all that chaos, thousands of different testing methods, and turn it into rock-solid consistency? It all boils down to this really simple but incredibly strict three-step process. First, you lock in all the parameters of the test, stuff like the cutting speed, the feed rate, how deep the cut is. Then, you run the test. And finally, you measure the wear on the tool using these very precise, agreed-upon methods. It's all about being methodical and repeatable. Now, maybe the most important piece of the puzzle is how you define wear. I mean, you can't compare apples to oranges, so the standard gives everyone a specific dictionary of damage. It lays out exactly what to look for, from flank wear, which is the most common, to other things like cratering or notch wear. Everybody is now looking for and measuring the exact same thing. And believe me, it gets incredibly specific. For that flank wear we mentioned, a super common failure point defined by the standard is just 0.3 millimeters. That's it. Once the tool's wear hits that tiny little measurement, the test is done. That one number brings so much clarity and consistency to a really complex process. Okay, so this all sounds a bit technical, right? But what does it all mean for the real world? Why should you care? Well, let's talk about the absolutely massive impact this one standard has. The reach of this thing is huge. We're talking about the most critical industries out there. Aerospace, where failure is just not an option. The automotive world, building the cars we all drive. Energy, medical devices. Basically, any field that depends on precision engineering is relying on the trust that this one standard creates. So the first huge benefit is for the companies themselves. With this standardized data, they can confidently compare tools from a bunch of different makers. It means they can pick the most durable, most cost-effective tool for the job. We're talking smarter purchasing decisions that directly affect their bottom line. Second, it helps engineers totally optimize their entire manufacturing process. Because they understand exactly how a tool is going to wear under specific conditions, they can fine-tune things like cutting speeds and feeds. And what does that lead to? Higher productivity, better quality parts, and a whole lot less machine downtime. And third, it's the absolute bedrock of research and development. When scientists come up with some revolutionary new tool, coating, or new material, how do they prove it works? They use ISO 3685. It gives them that credible, bulletproof validation they need to bring real innovation to the market. All right, let's wrap this up by looking forward, because this standard isn't just some dusty old document about today's factories. It's a critical foundation for the manufacturing of tomorrow. And this is what's so cool. This old-school standard is what makes cutting-edge technology possible. The super reliable data it produces, it's the perfect training fuel for AI models that predict when a tool is about to fail. It provides the baseline for monitoring systems that detect wear in real time. It's even how we prove that sustainable techniques, like using minimal lubrication, actually work. It's the launchpad for what's next. So, if you remember anything about ISO 3685, remember these three things. 1, it creates trust because the data is comparable. 2, it drives efficiency across all of manufacturing. And 3, it enables innovation for the technologies of the future. It's this incredibly powerful framework, just hidden in plain sight. Which kind of leaves us with one final thing to think about. What other invisible standards, what other hidden rulebooks are out there quietly shaping the world all around us?